Hey folks, it's Mr. Ray here with our next lesson in grade 12 data management. We are in unit 4 of the course, which is statistics. On our last lesson, we were looking at measures of central tendency, which had to do with the mean, median, and mode. Basically, where's our data centered if we sorted it, and that gives us a good characteristic of how to talk about the data or what it represents. So today, this lesson goes hand in hand with lesson 4. So now that we know how to find the central tendency or where the middle of the data is, we want to know how spread out the data is. So you could have, and we'll see this in an example, where you could have two sets of data that have the same mean or median, but one set of data might be very spread out. You might have values, say you had say your mean was 70, you might have one set of data that has a mean of 70, but the values are, all spread out from, 20 to 100. And the second set of data is with the same median or mean, but it's all very tightly centered around. So maybe everything's between 60 and 80. So those different data sets means something entirely different in terms of what they look like and what it represents. So today's lesson is on measures of spread, where we come up with some ways of measuring the spread of the data. Okay, now each of these measures will either be applicable to the median or the mean. So it's important to understand which one goes with which. So I'll just do a quick little summary here. The main median measurements we have are percentiles and quartiles. Don't worry about knowing what they are yet. I just want to put things in perspective first. And for mean, we have standard deviation and z-scores. Okay, and we're going to look at all of these things, but I just want to put that in your head right now. So when I do all my definitions and key concepts and examples, I do it in order, so that first we do all the median measurements of spread, and then we do all the mean. So just to keep it separate. So if I'm looking at the definitions here, and again, there's a lot of definitions here. Just let me zoom out a little bit. A lot of definitions. I'm not going to go through them all now. Kind of explain them as we come to each type of measurement. But for now, I want to show you that first we have the definition of measures of spread, and it's kind of what I said. This is the official definition: numerical values for a data set that indicate how closely the data cluster around its center. Okay, so these will be numerical, like it says there, numerical values. So get a number that will help you understand how close the data is to the middle. So that's just a general definition of measures of spread. And I start off, you can see with quartiles. We already know that's a median measurement. So quartiles, and we go down to percentiles, which you also know. So all these definitions at the beginning, they have to do with the median measurements. So all these apply to just the median. And the rest of them have to do with the mean. So deviation, we've already seen standard deviation, z-score. So I'm not going to go through these just yet. This would be a good thing for you to look at the end of the lesson. Make sure you understand everything that's here. But it's a little overwhelming to try to look at, just give you a bunch of definitions first. And likewise on the key concepts, you can see this is pretty overwhelming. We've got a full page of key concepts, lots of formulas with letters and things that we've never seen before. So rather than put a bunch of mush in your head, so what we'll do is we'll talk about these when we come to those questions in the example section. Okay, but again, these first two are more general concepts for all types of measurements, and then we have the median ones that go up to here, and then the mean measurements. Okay, and one thing, we will come back to these, I promise, but I just want to talk about the second one. There's something called the range. The range in terms of measures of spread is basically what's the lowest value in your data, what's the highest value in your data, subtract the two, that's your range. So the range in itself also gives you a little bit of insight into how spread out the data is, but not a real good insight, you know. So there will be an example where we calculate the range as well. So we will come back to these once we look at the examples. So we're going to start off with percentiles. I don't have, in terms of number of examples, I think I have 4. So there's 4 examples with multiple multi-step questions. Okay, so I didn't want to overwhelm you, but I wanted to focus in on those 4 measurements that you've seen at the top of the first page, and so you have an idea of how do you use them and what do they mean. Okay, so the first example here, I'll zoom back in a little bit. The list shows the marks for 25 students on a recent test out of 40. So we've got our marks out of 40 for all the students in the class. And we've got some questions about percentiles here. So, percentiles, I've already told you a couple times, has to do with the median. And the median is the middle mark, right? And if you remember from the last class, the last lesson, we always had to sort the data. So that applies also for percentiles. So before I can do any real calculations here, I'm going to have to order the data. And you have to be careful about this, because if you're not, it will totally mess up everything you do. So like I mentioned before, I've already got this list made out on a piece of paper, but when you're doing this, you basically go through and you look for the lowest, you write it down, cross it off, look for the next lowest, cross it off. You'll see some with duplicates, so make sure it's really important to just do one at a time, otherwise you're going to probably miss some of the duplicates. Okay, so we got 15, 16, 20, 21, 23, 24, 25, so we have actually got 3 of them, and then 26, and we have 4 28s, so I'll put 2 of them there, 2 of them here, then a 30, 31, 32, 34, 36, 37, 38. Oh, did I miss one here? 28, 28, 32, 36, 37, 38, 40. Let's make sure I've got the right number here. 15, 16, 26. Okay, I think I might be missing one. Just hold on one sec. Okay, yeah, I made a couple of little mistakes, but I've corrected it now. So we do have 25 entries. I think I left out a couple by mistake. They're all sorted. Highest is 40, lowest is 15, and there's a total of 25. So we can get going now. All right, so the first question, and there's really 2 types of questions you can get here. So the first one's probably the more popular type of question. Calculate the 80th percentile. So that we can actually have any number here from 1 to 100. Probably not 1 or 100, but usually it's in multiples of 5, like the 55th percentile or something like that. So what this means, percentile, if we go back to the definition, the percentiles divide the data into 100 intervals, and percent is 100, right? 100 intervals that have an equal number of values. So basically it's like slicing up your sorted data into blocks of 100. And obviously, in this situation, we've only got 25. So, you know, you wouldn't really divide it up into 100 blocks, but you'd find basically the position that's 80% of the way through the data. Okay, so what the 80th percentile actually means is it's going to be the mark that's higher than 80% of all the data. Okay, so 80th percentile means in terms of these marks that mark that we're going to calculate here is higher than 80% of the other marks. Okay, so we're going to need a couple things, parameters here. So if I go back to my formulas, which was the key concepts pages. So I've got two formulas for percentiles. Well, this first one is called percentile rank. So what that gives you is the position in your sorted data where that percentile is. So that's what we're going to be using on our first question. We want to find the actual mark that's the 80th percentile. So first of all, we have to find where in the list is that mark, and then go grab the mark from using that that order, that rank. Okay, so what we need here, we need P, and P is a percentile, so that's just for us, it's going to be 80. And we also need N, which is the size of the population. So I might as well put that up here because we're going to use that several times. That's 25 because it's 25 marks, 25 students. Okay, so if let's put that down here as well, just so we have it. P is 80 because we're looking for the 80th percentile. So our formula is capital R for rank is P over 100 times N plus 1. And let's see what this formula actually does. So the P 80 percentile, 80 over 100, well, that's basically going to turn into 0.8, which is the same as 80%. And then we multiply the number of data points, or number of, in this case, the number of marks, plus 1. And you might think it's kind of weird. Why are we using N plus 1? It's just, if we're trying to find the position, we need to increase this by 1. Otherwise, if we just use N, we wouldn't get the right position. So just trust me on this one. So when we plug the numbers in, 80 over 100 times 25 plus 1. So when we do that math, we get R equals 20.8. Now, what that says is the 80th percentile lies in the 20.8th position of our list. So I would be counting, not from this list, but from the ordered list, I'd be counting up to 20.8. And so obviously, what do you do with the 0.8? Okay, so if you do get a decimal in this calculation, what you do is you basically take the two values around it. So 20.8 means we're actually going to use positions 20 and 21 measurements. And we're just going to take the average of the two. Okay, so in our case, so we're not done here. We've got the position or the rank where the 80th percentile is, but now we actually have to go and find the 20th and 21st position in the list. So you just start counting from here 1 all the way up to 20 and 21, and that's actually going to be right here. So the 20th position or rank has a mark of 34, and the 21st has a mark of 36. So what we do when we calculate the percentile, when we have a decimal value for R, we take the two values around it and average them. So 34 plus 36 divided by 2, that's going to be 35. So in this data, the 80th percentile is 35, a mark of 35. So what that means is, like I said earlier, 80% of the marks are below 35. And remember, 35 is not percent, it's 35 out of 40, so that's a pretty good mark. Okay, so that's how you do that. I'm not going to do another example of that, but you're basically plugging your percentile here, your N here. Now, if you got say this was say you end up getting like an exact integer here. Say you got 22. You just go find the 22nd position and use that mark by itself. You don't have to do averaging if you have an integer value for r. Okay, so let's do the opposite process here. So instead of finding the percentile, or finding a certain percentile, we're looking at a specific mark and asking what percentile is that mark. Okay, and we're going to do two examples like that. So I'm going to show you. I'm going to write down the information I need. So first thing we do is we look. Okay, where's 25 on our list? So you go back up to the list and you start counting. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so basically, and you notice we got 3 of these 25s. You just go till you find the first one. So in our case, so we're looking for the rank of that mark. So the mark of 25 has a rank of 8. Okay, and then we look, and this comes naturally, how many marks are below this mark of 25? Well, it's everything to 1 through 7. So basically you subtract 1 from here and you can say there are 7 values less than 25. And I don't really have to go back to my list for that because I know anything below 8 is going to be less than 25. So I'm actually going to assign a value. We use a capital L. Okay, now I'm gonna come back to the formula in a sec. And the other thing we have to look for is, remember we mentioned there's 3 of these 25. So how's that going to affect our answer here? So since there are 3 values equal to 25, or duplicates if you want to call it that, equal to 25. So we have another variable. I guess it stands for equal. E equals 3. That's the number of duplicates. L is the number of entries less than what we're looking for. And now we can go ahead and use our formula, which we will find back on the second page. So we've already used this one to find the rank of a percentile, and this way we're going backwards. We want to find the percentile of a specific mark. So this is the formula here, and you notice we've got our capital L, our capital E, and a little n. The little n is the 25, and the L and the E we just wrote. So if I was to rewrite that formula, P is equal to 100 times L plus, I'll just put the formula first, 0.5 E times E over N. So we've got everything we need. We got our N from before. So that's 100. L is 7 plus 0.5 times E, which is 3, all over 25. So if we do that math, we get our answer of 34. Okay, now this is actually giving the percentile, right? Instead of the ranking. Okay, so this is our answer. It's asking what percentile is it. This formula gives the percentile. You don't have to go back to your list and start counting. So basically the answer to this, the question is, what percentile is a mark of 25? So therefore a mark of 25 is in the 34th percentile. Okay, and again, what does that mean? It means 34% of all marks are less than 25. Okay, the question didn't ask for that, but it's good to state what that actually means. Okay, we got a very similar question here, except we've changed into wanting to know what the percentile is for a mark of 25, we want it for a mark of 40. So very similar. So if we go back to our list, we're looking for 40, and 40 was that perfect mark. So so we know that's the 25th mark. So a mark of 40 has a rank of 25. Now we didn't actually use this number in the, that's 7 we didn't use. Sorry, the 8 we didn't use, but we used basically one less than this, right? We want to know how many marks are less than 40. Well, it's going to be 25 minus 1, because everything to the left will be less than. Okay, so there are 24 values less than 40, right? One, it's always one below what the ranking was. And then in terms of duplicates, there was only 140, so don't have to say this every time, I'm just doing it so you're understanding where it comes from. There is one mark equal to 40. So E equals 1. I forgot to say L here. L is 24. Okay, and then we just use the formula again. So we've got P is equal to 100. This time I'll just plug the numbers in. It's that formula right above here. So we've got L 24 plus 0.5 times 1, because E is 1 over 25 again. And that is equal to 98. So a mark of 40, therefore a mark of 40 is in the 98th, is in the 98th percentile. Okay. Now, you might have been thinking, well, if it's the highest mark, shouldn't it be the 100th percentile? Just remember what the definition of percentile is. It's a percentage of marks lower than that number that you're looking for. So it's never going to be 100. This is about as high as it can get. I guess it could go up to 99 points, whatever. But you know, for most data sets, you'll see that 98, 99 is the highest. Okay. Okay, let's continue on with example 2. So example 2, we are looking at the other measurement of spread for medians. So this is using quartiles. Okay, so there's quite a few parts to this question, different calculations. So let's look at some of the things that we're going to need to talk about, the definitions. So if I go back to the definition page, we've covered the percentages, so we're down to here. So quartiles, the next thing. Well, basically quartiles is very similar to percentiles, but it's actually a lot easier to work with, because instead of doing like percentiles, divides all the data or marks into 100 equal slots. Quartiles only have 4. So they're basically the first quarter of the data, the second quarter, the third quarter, the fourth quarter. Okay, and we have some special terms. So the position, or the value that is at the quarter mark of the data, if we sorted it, so basically a quarter from the bottom, that's called Q1 for first quarter, and that's exactly the same as the 25th percentile. So you could just change these questions, change Q1 to 25th percentile. It would be the exact same answer. Okay, So Q1 is a quarter of the way through it, or 25% of the way through. Q2 is halfway through. We don't use Q2 very often because we have another name for Q2, and that's the median. Okay, so 2/4 of the way through the data is halfway through the data, which is what we're calling the median. So we can call it Q2, but you won't hear it referred to very often. And Q2, or the median, is the same as the 50th percentile. And then Q3 is going to be 3/4 of the way through the data, or the 75th percentile. Okay. Now we have these three formulas for Q1, Q2, Q3. Again, these are for the positions or the rank. What position in the list is? We just count up in the data that's sorted and see what the value of Q1 or Q3 is. Okay, so that's how we do that. And then we have something called the interquartile range, IQR for short. And that's just a very simple, you've got your Q1, you've got your Q3, and you subtract them, find the difference. And if you think about it, this is 75% of the way through, and this is 25% or quarter. So the total amount of data between Q1 and Q3 is always going to be 50%, or half the data. So that interquartile range, like it says here, contains 50% of the data. So if that number is small, it's telling you that the middle 50% of the data is, close together, or if it's large, it's telling you it's far apart. So that number by itself, interquartile range, actually tells you quite a bit about how compressed or spread out the data is. Okay. So we're going to be working with these. We're also going to look at this formula, but I won't talk about that yet. So let's go back to the question. The table lists the heights of the 20 girls who signed up to try out for the school basketball team. So we've actually got some ranges of heights, unfortunately. So this is group data. So it's important to have an example of group data to see how we handle that, because it is different. So the coach, I guess, has put together the list of the tryout players, and basically assigned how many girls were in each of the ranges for the height. And if you remember a few lessons ago, I basically said when you give a range for groups, you shouldn't have the possibility of having the same used value at the beginning and end of sequential ranges, like the 160, 165, etc. And I still firmly believe in that, but sometimes you get data that's already arranged for you, and you just work with it. So it won't be a problem here, but if I was creating these groups, I definitely wouldn't have done it this way, just for the fact of, where would you put a girl that had a height of 165? Do you put them in this group or this group? Because both groups have the same height, so it's a little confusing. So we'll just kind of ignore that, because sometimes you can get data that's not the way you want it. So we've got the frequency, number of girls in each height group, and then cumulative frequency. We've seen this before when we were looking at our graphing in the first lesson. For the histograms, this was used sometimes. It'll actually be more important for this. Okay. So part A, it's asking all sorts of information: the median, the range, the first and third quartiles, interquartile range. Okay, we covered all those, and then it's asking us to create something called a box and whisker plot. So that sounds interesting. So rather than define what it is, I'll just show you what it is when we get to that point. Okay, so the first part, I'm going to divide this up, is we want the median. Now, the first thing we should do is figure out how many girls there are. Well, there's 20. So this column should add up to 20, and it does. And that's your value of n. Okay, we don't really do a total here because it comes from the frequency, so it's not used at all. So we're actually going to calculate the median position, So it won't be the actual median, but it'll be how far down the list do we look for the median. So if you remember, the formula was for the Q2 or median, 1/2 of n plus 1. So I might as well just put the 20 in, save some room. So 1/2 20 plus 1 is 21. Half of 21 is 10.5. Okay, so again, just like that question we had on the last example, we've got a position that's like a decimal. So just like we did last time, we're going to look at positions 10 and 11. Okay, because we got a number in between two integers, two positions, so we actually average both the positions around that value. So how do we find that? So we actually go up to the list. Now this is where cumulative frequency is very useful, where it wasn't before. So we're looking for the 10th and 11th. So it's not in here because there's only the first one here. The first, so we've only, this goes up to the 4th position. This goes up to the 8th position. We're looking for 10, 11. This goes up to the 15th position. So the 10th and 11th positions are both in this grouping. Okay, so I'm actually going to maybe go over here, and that's Q2, so, or median, either way. So Q2 is in this group, and you notice 10, 11 are both in there, so I don't need to look in two different groups. It's the same group. Now the other thing I'm going to need here is the midpoint, just like we did before, because you could ask yourself at this point, well, I know it's in the 10th and 11th position, but what value do I give that? So we're going to do the midpoint here. Okay, and the midpoint is just the average of the two, so it's very easy to do. So 157.5, and it goes up by 5s. 162.5, 167.5, 172.5, 177.5, 182.5, 187.5, and 192.5. So it's just taking those two values, add them together, divide by 2. So we know that Q2 lies in this group. So what value do we give the median? We give it the midpoint. Okay. So for this, now that I know the position, I can find it on the groupings. So the median is equal to, so that group had a midpoint of 172.5. And don't forget the units, because that what we're indicating here is the height in centimeters. So the median height is 172.5 centimeters. Okay, so there's our first one. It also wants to know the range. Range is a super easy one to do. So you find your highest and your lowest value, subtract them. So then the question becomes, do we use our midpoints? Because I know the lowest value is in here, the highest value is in here. Should I use 195 for the highest? Should I use 155 for the lowest? Or should I use the midpoints? And the answer is use the values at the end of your groups. So it's going to be 195 minus 155, which is 40 centimeters. So your range of data, basically that's the difference between the tallest person and the shortest person that's listed here. Okay, let's do the third one, which was our Q1 position. We want to know Q1. So first we find the position, and it's very similar to the formula we use for the median. Median's also Q2. It's 1/4 of the way through our data. So that's 1/4 times, basically here it's going to be 21 again. So when I do that math, I get 5.25. So it's position number 5.25, which makes no sense. So we use positions 5 and 6. Okay, so now again we go back up to our chart, cumulative frequency. Once you've done this a couple of times, it's very fast. So where does the 5th and 6th positions lie? Well, it's not there because that's only up to 1. That's up to 4, so it's not there. That's up to 8. So this contains positions 5, 6, 7, and 8. They're all, both of our values are in there, so that's our Q1. So in terms of Q1, that's equal to, and again, we use the midpoint for our quartile numbers. So Q1 would be 167.5 centimeters. Okay, next thing we want is the third quartile. I'll do that up here. So we want to find the position. Hopefully this is making more sense. So it's like we did for Q1, except instead of having a quarter there, we use 3/4. So 3/4 of, at this point I'll just put 21 because it's always going to be 21, 20 plus 1. And that's equal to 15.75. So again, we use the integers around that number, 15 and 16. Okay. All right, so now we go try to find 15 and 16. So it's not there, it's not there. This goes up to 15. So the 15th position is in this group, and the 16th is in the next. So I'll just show that here. So I'm going to show both groups. That's where Q3 is. Okay, so how do you handle it when it straddles two groups like this? So let's just write this, Q3 equals. So what you do in that case is you could average the two, I guess. Yeah, that would work as well. But we just picked in this case, the value that they both have in common, which was 175 centimeters. Either way would work. So there's your Q3. So now we've got basically median, Q1, Q3, and last thing is the interquartile, IQR. That's equal to what we just got for Q3, subtract what we just got for Q1. So that's 175 minus 167.5. That's equal to 7.5 centimeters. Okay, and that's all the numbers we wanted. Now we actually use these to create something called a box and whisker plot. So that's an interesting name for sure. So this is going to be a visual representation of what we just did here to give you a better perspective of what's going on with the spread of the data. So we always start off with the horizontal axis. Okay, and you look at your potential data. So it goes from 155 to 195. So I'm just going to start at 150, which is slightly below. I'm going to go up in blocks of 10. So 170, 180. I guess I should spread that a bit, or compress it a bit more. I want to be able to go up to 200 since the highest on the chart is 195. Okay, so we'll maybe go here, 160, 170, 180. Okay, so that's better. And I'm going to put a little title because it is, should be treated like a graph. So I'm going to put the height in centimeters. That's what these are representing. Okay, so let's see how this works. So we start with the box part, and then we do the whiskers. Okay, so each of the Q1, median, and Q3 are going to be part of the box. So the way you do it, I'll start with Q1 because that's the lowest number. And I guess I'll put little notches for the 5 values just for now so I can see where to draw these lines better. So 167.5 is halfway between there and there. So I'm going to go up a little bit. I'm just going to draw a little vertical line. Okay, so that represents Q1. Then I'm going to do Q2, which is median. Median is 172.5. 172.5 is halfway here. and I'm going to draw a vertical line at the same level and same height as the Q1. So there's Q1, Q2, and then Q3 was 175, which is right here. Same idea, vertical line. Okay, so you got your Q1, Q2, Q3, and now you do your box. So this is basically, I just set myself up so I could do a rectangle. So the lower edge is Q1, the upper edge is Q3, and the line in the middle is the median. That's the box part of the box and whisker plot. Okay, and then what we do is we find the lowest value, the lowest and the highest, and we do the whiskers. So in this case, do we know the lowest value? Well, not exactly, but we do know it lies somewhere between 155 and 160. So we assume that it could be 155, so that's where we're going to draw our next. So another vertical line, same level as the box was here, and then we do one for the maximum too. So again, there's one entry in between 190 and 195. We assume that it could be the highest, so we do one for 195. So again, I put a line there, and here's the whiskers. So we're not going to join these using like a box. We're going to draw a line from the middle connecting to the box for both of them. Okay, so there's our box and whiskers. So like I said, there's Q2, median, Q3, and that's showing exactly where the center of the data is. It's also showing how compressed each of these quarters are. You can see that the third quarter is more compressed. It has more of the same values, more values closer to the median than the second quarter of data. And then the first quarter and the last quarter are pretty spread out. Okay, so it says describe the data in each zone of the plot. Well, all that's saying is here's one zone, here's the second zone, third zone, and fourth zone. Each of those zones is 25%. So 25% of data are in each of the four zones. Okay, so for sure you're going to be asked to do one of these. So just practice it. One thing that the most common mistake I see with the box and whisker plots are these scales aren't to scale. So you have to do this, and it has to be, the same distances between. You can't just start looking for these values and plotting them. That won't show the relative compression if you just don't worry about your scale here. So don't even look at the data. Do this scale. You have to make sure you have the highest and lowest values, and then you do your Q1, median, Q3, box around it, and then you do your lowest value, your highest value, whiskers to them. Okay, now the last part says identify any outliers. So what an outlier is a value you have in your data that seems abnormally too small or too big. Okay, and this can happen for a variety of reasons. Could be somebody made a mistake, or a measurement was made incorrectly, or maybe it's actual real data. We don't know. So sometimes what we do is we try to find if something is an outlier. And it's pretty hard for this, but if you had actual data and you had a series of marks where all your marks, maybe a test, but, maybe everything was between 45 and 90, but you had one mark of 12, right? That would be considered an outlier. If you plotted those, the 12 is so far away from all the other marks, you would consider that an outlier. Okay, so there's an actual way of determining it. In the past, I've just kind of eyeballed it to see if it looks ridiculously high or low, but there's a formula here, right here. It says An outlier exists if its value is less than, and so this will be the lower end. So you could see what the lower end of the range would be before you start considering it to be an outlier. So you look at your Q1 value, which we've got, you subtract 1.5 times the IQR, interquartile range. Whatever that value is your lower end. So if you saw any marks below that, it would be an outlier. And then at the upper end, very similar looking formula. You start with Q3, and this time you add 1.5 times the interquartile range. You'll get a value here, and if you see anything above that, that would be considered to be an outlier. So we're going to do that here. So the lower end would be Q1 minus 1.5 times IQR. So our numbers are Q1 was 167.5. Our IQR was 7.5. When we do that math, that gives us 156.25 centimeters. So if we see anything lower than 156.25, that's going to be a problem. So let's just wait. Let's do the upper one as well. So the upper value before it becomes considered to be an outlier is Q3 plus 1.5 times the IQR, and that's 175 plus 1.5 times 7.5. That works out to 186.25 centimeters. So now we can go back to our data. If we see anything smaller than this or larger than this, it will be considered to be an outlier. Our lower range is 155 to 160, and we're looking, is there anything 156 or below? Well, it could be, but what we're going to base our numbers on is the midpoint, okay? Because we don't know what the actual values are. They weren't given to us, so we use our midpoint to determine if it's, so our lowest mark is considered to be 157.5, which is higher than that, so it's good. And then our upper mark, there's only one here, and it's 192.5. Well, that is higher than our upper end of our valid data. So I would say, therefore, one outlier at 192.5 centimeters exists. Okay, and once you've identified it, sometimes in studies, if you see an outlier, you might just ignore it because it really changes the data, the characteristics of the data. Sometimes you would keep it in, so it sort of depends on the study that's going on. Okay, so those are the two examples using the median. So we looked at percentiles and quartiles. Now we're going to look at comparing data using mean, and in this example we're going to look at standard deviation. Okay, now this is the type of questions you're going to get in the last unit. When we look at the normal distribution, it's going to be exactly this type of question again. We're going to go a bit deeper into it then. So let's take a look at this. So in this example, we've got two basketball teams, Falcons and the Ravens, and we've got our 7 girls on each team and their height. So similar to the last question, except this time we've got individual specific data. Okay, so we can actually calculate the mean on this one instead of the median, because we're going to take the average of all these values. So it says use means and standard deviations to compare the distributions. So we're going to calculate the mean for the Falcons, standard deviation for the Falcons, same data for the Ravens, and use that to compare what those two teams look like, or how How are they similar or different? Okay, so the first thing I would do is count the number of players. So I've got n equals 7, n equals 7. They both have 7 players. Now, when we do our calculations, it wouldn't be a problem if this was n equals 8. We just do it totally separate calculation for each team. So it's just a coincidence that they both have the same. So in this, you can see I've got a couple extra columns that we're going to use. I'm going to call this data, which is the height. I'm going to call that x. Okay, and we're actually going to sum up the heights. When we do that, we actually get the exact same value, 1155 and 1155. Okay, and if you remember calculating the mean, you take this, when you add up all the values, you divide by n, you get x bar. So in this case, x bar is 165. And also, since this is the same total with the same value of n, this is also the same. X bar equals 165. Okay, so we've actually finished half of what we want. But you can tell, this is actually from the last lesson, calculating the mean. Now we're calculating the standard deviation. So let's see how you do that. So I've got these two columns for a reason. So I'm going to put something called deviation here. Now that's not standard deviation. This isn't our final total. And then something called variance here. And I'll put it at the top for both. Deviation, variance. Okay. Now the deviation formula, it's basically how much does each girl's height deviate from the mean. So it's just subtracting each girl's height, subtracting the mean from each girl's height. Okay, so the first one would be, we know the mean is 165, so 183 minus 165, that's 18. That tells you that this girl is 18 centimeters taller than the mean. Okay, now negative numbers are important, at least for this column, because it would show that some girls are less than the mean, and you can't have some girls being above the mean without having some girls below the mean. Otherwise, the mean would be wrong. So when I go through all these, you can see this girl is exactly, her height is the mean, so the deviation is 0. This girl's less than, she's minus 17 centimeters below. So if I continue on with this, you can see some girls are negative values and some are positive, depending on their specific height. Okay, so if you actually add these deviations up, you should get 0, because they should all even out. If I do the same thing down here, this time I'm, so I guess I should have put the formula here. This was x minus 165. This was x minus 165 also. So same process here. This girl's 166, so her deviation is 1. Next girl was 2 lower, positive 3, negative 4, 0, 1, 1. You can see that this team, their heights are very close to the mean, where these girls had heights that were further away. So that's what we're measuring here when we measure the spread, but let's get an actual number that we can use. Okay, so again, when we add those up, we should get 0. This last column here is called the variance. So the variance is, it's very simply, I take the deviation and I square it. So maybe I'll just put that up here, deviation squared. I could write out the formula. It's just bracket x minus x bar, bracket squared, but we're just taking these numbers and squaring it. So when I go through that, obviously when you square a negative number, it's positive, right? So we're only going to have zeros or positive numbers here, no negatives. So I'll just write 18 squared is 324, 0, 289, 361, 256, 169, and 121. Those add up to 1520. Okay, so we're going to be using that number. We're not done yet. We just had to get this. This was the important number to get. Okay, now we do the same for the other team. You're going to see these are lower because when we square it, they're not nearly being as big as those. So I've got a 1, a 4, 9, 16, 0, 1, 1, and that total is 32. So that's quite a bit smaller than the other team. Okay, so let's kind of put our data to use here. So Falcons. All right, so if you remember the mu, okay, you probably don't know what I'm talking about when I say that. I go back to these formulas for yeah, so when I used the population, when I was analyzing the population, my average was, we called that the letter mu. Let me put that out here. MU, or sound a cat makes. That's called mu. Whereas if we were looking at a sample, we use X bar. Okay, and we're going to see this as standard deviation. Let's look at that formula right now. So we got our formulas, and you can see the variance here compared to the standard deviation. This is exactly the same, except I'm taking the square root, and that's what we're going to do. The big difference in the formulas here are, when I'm calculating the standard deviation, if I'm looking at these two formulas, I've got different letters here. Okay, this is another Greek letter called sigma. Okay, you don't have to say it, you just have to know that it's a variable that represents standard deviation for a population. Whereas for the sample, we use the English alphabet letter S for sample, I guess, standard deviation. So those two don't matter too much, okay? But what matters is the rest of the formula. You can see the top part's the same. I'm using, my mu from my population, or I'm using my X bar from my sample. Now, what's different are these two. So you have to be aware of this. If you're calculating the standard deviation and you have all the population represented, then you just use the population, n. Okay, but if you're calculating standard deviation and you're just looking at a sample of the population, then you divide by n minus 1. So this is going to be a little bit smaller, which is going to make your standard deviation a bit bigger. Now, why is this true? Well, this is, if you just take statistics from a sample, you're going to be prone to have some errors there. It's not going to be exactly the same as the population. So think of this n minus 1 as kind of a correction factor. But you can see the only difference is, the n values really mean the same thing. It's the number of data points. But here we subtract 1, which will give us a bigger standard deviation. So make sure you know, am I looking at data for a population or for a sample? So when we're doing these basketball teams, is this a sample of the basketball team or is it population? Now it doesn't say that it's a sample from a basketball. These are the only 7 players on the basketball team for the Falcons. These are the only 7 for the Ravens. So in this case, we're actually working with a population. So our formulas should reflect that. So when we do our formulas for standard deviation, we're going to use the n on the bottom, not n minus 1. Okay, so let's get back to where we were. So in this case, since this is a population, okay, our mean, we're going to call that mu, which is basically what we calculated with our x bar. Now I could have called that mu at the time too. It's okay if you call it x bar here, but once you realize you're working with a population, you can call it mu. Okay, so these two are the same, and we've already calculated this. It's the sum of the x's divided by n, which was 165 centimeters. So this was our mean. Okay, now when we do the standard deviation, we're going to use the sigma symbol and that formula. So I'll call it what it is. Sigma equals, so the formula looks like this. I'll just sum of x minus x bar. Actually, no, it's, yeah, let's keep it as x bar since we called it x bar there. Squared over n. Okay, so what we've actually calculated here, this 1520 and this 32, so for this calculation, the sum of this up here is the 1520. So it's not as scary as it looks. This gets replaced with our sum of our variances. Okay, so that's 1520 over n. Our population was 7, and that works out to 14.7 centimeters. So that's the standard deviation. Okay, hopefully I'm not confusing it too much, but you can see how you get the data from the table, and you're really just plugging in the sum of the variances as your top part here, divide by n, and then take the square root, and there's your standard deviation. And let's do the same thing for the ravens. So our mean is, I guess I should have put those in, but it was also 165. We did that earlier. So exactly the same mean, but the standard deviation will have a different formula. So this time, instead of 1520 on the top, we're actually putting in 32. So you can see it's going to be quite a bit different, smaller. And in fact, it's 2.1 centimeters. Okay, so if you're comparing these two teams now, and the whole point of doing this is so you can have a good understanding of what these two teams look like in terms of their height, you can definitely say what we knew earlier. Both teams have the same average height. Of 165 centimeters. But the Falcons have a much So I remember the Falcons team, that was the one with the bigger standard deviation. So that means the girls on that team have a much bigger spread of height. Falcons have a much greater spread. $14.7 compared to the Ravens. And their spread was 2.1 centimeters. Okay, and you're probably thinking, well, I could have told you that just by looking, just by looking at that. You can just scan by here, and they all start with 1.6 for the Ravens, but these ones are quite, you got some 1.8s, 1.4s, so quite a bit spread out. it's going to be very important on the next unit to be able to do these calculations. So for this unit, I'm going to be asking you what's the standard deviation and mean, so that you can actually have a numerical comparison to compare two things or talk about them. And then that skill you're developing with this question will be used widely in Unit 5. So this is our first measure of spread using standard deviation. Okay, now we also have something called Z-scores, or as people from the US call them, Z-scores, or as people who watch YouTube call it, Z-scores as well. So either way is fine. So we're going to figure out what this a Z-score is. So let's go look at, do we have a definition for this or not? Sure we do. Okay, so the first page. So the Z-score will be a number that we get. Okay, so that number is the number of standard deviations that a data point is from the mean. And we're going to work with Z-scores a lot next unit as well. But basically the data, I think it's 99.5% of all the data will be within three standard deviations. So plus or minus 3 standard deviations, that's the range of all data. So, or 99.5% at least. So when you say something has a Z-score of, say, 0, that means it's right at the middle. Okay, so you're looking for a Z-score of a particular data point. If you had a data point that had a Z-score of -3, that means it's right at the lowest end of the data. A plus 2.5 would be very close to the top, etc. So we're just looking at those raw Z-scores for now. We're actually going to use them to our advantage next unit. But a Z-score is basically a scale of pretty much -3 to 3 that tells you how far away from the middle a piece of data is. Okay, so I've got a question here. A food manufacturer makes 2-liter jars of pasta sauce. Samples are tested for how close the 2-liter jars are filled. 15 samples were taken and their volume and liters were, and then I just list them all here. And I've created a chart here just to show you what we're going to do. So one thing you notice right away, these are samples, right? So unlike the last example where the basketball team was the population, now we're looking at samples. So that would affect, if we were to do a standard deviation for this, that would affect how we do it, because our formula would be n-1 on the bottom instead of n. Okay. So I'm just going to show you a couple of these, and then I'm going to pause the video and fill the rest in. So first thing we're going to do is figure out what the mean is. So we get the mean from basically adding all these pieces of data up. So the sum of all the x values, the jar volumes, is 30.22. Okay, and how many samples did we have? Did it say? It's 15. So n is 15, and that sum is 30.22. That's all we need for the mean. So in this case, it truly is x bar because it's a sample, is equal to the sum of all the x over n, which is 30.22 over 15, which is 2.0147 liters. So that's our mean. And what we're going to do now is use the mean to help us do this. So remember the deviation we did on our last example? that's going to be the x value minus x bar. How far away are each of these values from the mean? Okay, so in this case it'd be 2.11 minus the deviation. So this is a little bit bigger. It actually works out to 0.0953. Okay, and then the variance, remember you take the deviation and you square it. So whatever that value is, I'm squaring it. So it's unfortunate when you get a low number like this, a decimal. When you square a low number like that, you get an even smaller number. So I'm going to be as accurate as I can. I'm going to put lots of decimal places. 0.009088844. Okay, and I'm going to do that for each of these. So basically, this number minus x bar, which is that, and then we square it. So I'm going to pause the video. I'm going to fill in the rest of the table and come back. Okay, and through the magic of the pause button, I've very quickly filled out the rest of the table. You can see how many decimals I put, and that was just because of how small these deviations were. Okay, one thing I didn't mention, a lot of times you're going to see the same measurements in your list, so obviously they will have the same deviation and variance, so save yourself a lot of time. Once you see one that you've already done, just fill in the same values. Once I finished, if you add these up, I actually got really, really close to zero. I think it was off by like, 1/10,000th or something like that. So just through the process of rounding it, you might be off by a little bit. Okay, and then I did the variance, and we don't really need that zero there other than just to check that it should be close to zero. But this is the value we're looking for to proceed. So the sum of the variances is what we're going to do to calculate standard deviation now. Okay, and now since this is a sample, if we go back to my formulas, right, now I want my sample standard deviation, so now I'm going to use the little letter s, and on the bottom over here I'm going to use n-1, which was different than I used on the last example. Okay, so s is equal to, and then on the top within the square root, I've got my sum of my variances, x minus x bar squared, and this time over n-1. Okay, so in terms of plugging those numbers in, the top is sum of the variations is the number we got there, 0.717733. n-1, well, n is 15, so n-1 is 14. And when I calculate that, I get 0.0716. Okay, and that is the standard deviation. So we've got the mean, we've got the standard deviation. And we're going to use that for the remaining 3 questions because we need those 2 values to calculate the z-score. So we don't know how to do that yet. So let's go back to the key concepts. And these formulas are a little simpler, and thankfully. So the z-score always starts with a little z. And you can see again, we got a different formula for the population of the sample. It's not a big difference here, it's just the different variables. So it's basically, the x is the value you're trying to find the z-score for, so that will change every time. Your mu or your x bar, that's your mean, and then your sigma or your s is your standard deviation. So in our case, we are working with a sample, so we're going to use this formula. It's not going to make a big difference if we messed up, but let's be official here. So the formula was the z-score, or z, is equal to x minus x bar over s. So we've got our S, we've got our X bar, and in this case, the question is calculate the Z-score of the jar that was filled to a volume of 2.02 liters. So that is our X value. So 2.02 minus, and then our mean, which was all the way up here, 2.0147 all over S, 0.0716. That is equal to approximately 0.0744. So what does that mean? Well, it means it's, because it's positive, because it could be either positive or negative. Remember I said the range of the Z-score should be somewhere between -3 and +3. So the fact that it's positive tells you it's on the right hand end of the distribution. So that tells you that this is above the mean, which is easy to check, right? Just the fact that it's 2.02 and the mean was 2.00147. You would have known that just by looking at that. But it also tells you that it's in one standard deviation above the mean. Okay, so we can interpret that, which it's asked for here. Therefore, the volume, the jar's volume is, and I'll use the number here, 0.744 standard deviations more than the jar, sorry, more than the mean volume, which is sort of what I just said. This would be the official way to say it. Okay, the next question. And now we have a different jar. We want the Z-score of the jar that was filled with a volume of 1.89 liters, and then compare the distance from the mean to that of the 2.02 bottle in part B. So this time, Z equals X minus X bar over S. So everything's the same except we change X to 1.89. So 1.89 minus 2.0147. So right away you can see that's going to be negative over 0.0716. And that's approximately negative 0.4842. Okay, so there's two things to get from this. The fact that it's negative tells you it's to the left of the mean, which means it's lower than the mean. It also tells you it's within one standard deviation, about half a deviation lower. So I'll do the same thing I did last time. Jar's volume is now I'm taking off the negative sign, but I'm going to say 0.482 standard deviations less. So this one was more than, this one's less than the mean. Now I didn't really answer this question here. Compare its distance from the mean to that of the 2.02. So this, it's really saying, is this jar further away from the mean than this jar? It's not really talking about what side of the mean, but this is 0.0744 away. This is 0.48. So obviously this one is closer to the mean. So this one is further from the mean than the 2.02 liter. Oops. Okay, try to cram that in there. Okay, and here's another type of question. I actually think this one's more fun. The manufacturer rejects any jars that are filled to less than 1.5 standard deviations below the mean. So in other words, if the jar doesn't contain a certain amount, which we're going to determine, it's going to be rejected. Nobody wants to buy something less than advertised. Obviously, if it's filled more than the mean, customer would be happy, so the company will be happy. So we're going to call this thing the reject volume. And the way we calculate that, so it's 1.5 standard deviations below the mean. So we're going to start with the mean, x bar, and then we subtract 1.5 times the standard deviation. So now let's plug in the numbers. So x bar, that was 2.0147 minus 1.5 of s, 0.0716. That's equal to 1.9073 liters. So that's the cutoff. So basically the company's saying anything with less volume than this number is going to be rejected. So if we go back looking for anything less than, unfortunately these aren't ranked or sorted, but anything less than 1.90, I think we saw, yeah, there's a 1.89 here. This one will be rejected, and that's it. So that level would mean that the jar with 1.89 liters would be rejected. Okay, so that's our example working with z-scores. You can still see it's, we still use standard deviation, but it's kind of like a different unit than standard deviations. It's converted into something that's more universal, because every sample or population is, all the data is within plus or minus 3 standard deviations, whereas, within 3 z-scores, but they could be farther away than that in the data with just looking at standard deviations. So I think I'm rambling here. So we've got some questions here for you to practice. I apologize for the fact that this was so long, but I think if we organize the lesson like this, I think you'll understand the types of questions you can be asked and how they fit together and relate back to mean and median. So using the central tendency from lesson 4 and the measures of spread, what we're talking about today, you can get a very good picture of what your data looks like, and be able to talk about it and compare it to others. So that's it for today. We'll have 2 more lessons. They'll be a lot less intense than the last 2. And like I've said before, these last 2 lessons are very important for Unit 5. So if you have a good understanding, that's going to be half the battle for the next unit. Okay, have yourselves a great day. We'll see you in the next lesson.